The controlled dampening that would transform automotive stability forever began its first smooth compression on the test track at Gabriel Manufacturing on October 15, 1901. Claude Semmens, the brilliant mechanical engineer who had spent months perfecting the hydraulic system, felt the revolutionary difference as his prototype automobile absorbed road impacts that would have sent any conventional vehicle bouncing dangerously out of control. "Gentlemen, we've just eliminated the automobile's most dangerous instability problem," Semmens announced to the assembled Gabriel executives as the experimental vehicle's hydraulic shock absorbers controlled wheel movement with mechanical precision that no spring-only system could match. For the first time in automotive history, wheels remain in contact with the road surface during impacts, providing consistent control and preventing the dangerous bouncing that has caused countless accidents. Claude Semmens' hydraulic shock absorber represented the first successful solution to automotive wheel control, replacing the primitive spring-only systems that allowed wheels to bounce uncontrollably after hitting road irregularities. The innovation would transform not just vehicle stability, but establish the foundation for all modern automotive handling and safety systems. The engineering achievement was revolutionary. Semmens had created a hydraulic system that could control spring oscillations while allowing necessary wheel movement, solving the fundamental problem of uncontrolled wheel bounce that made early automobiles dangerous to operate at any significant speed. Most significantly, shock absorbers would prove to be one of automotive engineering's most critical safety innovations, enabling the development of reliable high-speed driving and the precise vehicle control necessary for modern automotive transportation. If you love discovering the untold stories behind automotive history's most incredible innovations, please like this video and subscribe to the Car Chronicles. 1885–1900. The Wheel Bounce Terror. For the first 15 years of automotive history, driving faster than walking speed meant risking loss of control from violent wheel bouncing that could throw vehicles off course or completely airborne. Early automobiles used simple spring systems copied from horse-drawn vehicles, which allowed wheels to bounce uncontrollably after hitting any road irregularity. The physics of uncontrolled wheel bounce were terrifying and unavoidable with spring-only suspension systems. When a wheel hit a bump or pothole, the spring would compress and then rebound with tremendous force, often launching the wheel completely off the ground. Without tire contact, steering became impossible, and vehicle control was lost entirely. Early automobile wheel bounce was genuinely frightening for drivers and passengers, recalled automotive pioneer Charles Duryea. Hitting even small road irregularities at moderate speeds could send the entire vehicle bouncing like a child's ball. Many drivers simply refused to exceed walking speed because faster travel meant losing control of the automobile. The bouncing problem was particularly severe because early roads were rough, unpaved, and filled with obstacles that would compress springs violently. Every stone, rut, or bump became a potential launching point that could send vehicles into uncontrolled oscillations lasting several seconds. Driver fatigue was another serious consequence of uncontrolled bouncing. The constant jolting and unpredictable vehicle behavior made driving physically exhausting and mentally stressful. Many potential automobile buyers chose horse-drawn vehicles specifically because they provided more comfortable and predictable transportation. Tire wear was accelerated dramatically by wheel bouncing. Tires that repeatedly left and struck the ground suffered damage that reduced their already limited lifespan. The cost of frequent tire replacement made automobile operation expensive and impractical for many users. Vehicle mechanical damage was also common from the violent impacts caused by uncontrolled wheel bounce. Chassis components, steering linkages, and body panels suffered stress that led to frequent breakdowns and expensive repairs that made automobile ownership problematic. Most dangerously, wheel bouncing often caused complete loss of steering control at critical moments. Drivers attempting to avoid obstacles or navigate turns found their steering wheels useless when bouncing wheels lost contact with the road surface, leading to accidents that might have been prevented with proper wheel control. 1895–1900. Early dampening experiments. Recognition of the wheel bouncing problem led various inventors and engineers to experiment with methods of controlling spring oscillations and maintaining tire contact with road surfaces. These early attempts used mechanical friction devices and primitive hydraulic systems with limited success. Some inventors tried leather friction devices that would rub against moving suspension components to reduce bouncing. While these systems provided some improvement, they wore out quickly, required constant adjustment, and often made suspension movement too stiff for effective road irregularity absorption. Mechanical snubbers using rubber blocks or metal friction plates were also tested, but these systems were either ineffective at controlling bouncing or made rides so harsh that they created different comfort and safety problems. The balance between bounce control and ride quality proved difficult to achieve with primitive mechanical systems. European manufacturers began experimenting with crude hydraulic dampening systems in the late 1890s, using oil-filled chambers with simple pistons to resist spring movement. However, these early hydraulic systems were unreliable, expensive, and often leaked oil that attracted dirt and caused system failures. Early shock absorber development was largely trial and error, explained automotive historian David Lewis. Engineers understood that spring oscillations needed to be controlled, but the mechanical solutions required innovations in fluid dynamics and precision manufacturing that took years to develop effectively. American inventors focused primarily on mechanical solutions due to the country's emphasis on simple, reliable automotive components that could be manufactured cost-effectively and maintained by ordinary mechanics with basic tools and skills. The challenge wasn't just controlling bouncing, it was creating systems that would provide consistent dampening while remaining reliable under the harsh conditions of early automotive operation, including poor roads, extreme temperatures, and minimal maintenance capabilities. By 1900, the need for effective wheel bounce control was becoming critical as automobile speeds increased and road conditions remained challenging. The solution would require sophisticated engineering that combined hydraulic principles with practical automotive applications. 1900–1901, Gabriel's Engineering Challenge. Gabriel Manufacturing Company, established as a supplier of pneumatic and mechanical components, emerged as a leader in shock absorber development under the direction of Claude Semmens, an experienced mechanical engineer who understood both hydraulic principles and automotive requirements. The challenge facing Semmens was enormous. Create a hydraulic system that would control spring oscillations effectively while remaining simple enough for mass production, reliable enough for automotive service, and affordable enough for ordinary automobile buyers. Semmens' breakthrough insight came from studying locomotive and industrial machinery dampening systems, which had solved similar problems of controlling mechanical oscillations using hydraulic resistance. However, automotive applications required different solutions due to weight limitations, space constraints, and cost considerations. The key innovation was Semmens' development of a double-acting hydraulic cylinder that could resist both compression and extension movements of automotive springs. The system used oil flowing through calibrated orifices to create consistent resistance that would control spring movement without preventing necessary wheel travel. Semmens' double-acting design was brilliant in its mechanical efficiency, noted automotive engineer Henry Leland. The system provided dampening in both directions of spring movement while using relatively simple hydraulic components that could be manufactured reliably and maintained by ordinary mechanics. The hydraulic oil and sealing systems required significant innovation to provide reliable operation under automotive conditions. Semmens developed oil formulations that would maintain proper viscosity in temperature extremes while creating seals that could prevent leakage during thousands of compression cycles. Mounting and integration with existing automotive suspension systems required careful engineering to provide effective dampening without interfering with normal suspension operation. The shock absorbers had to be positioned and designed to control wheel movement, while allowing necessary suspension travel for road irregularity absorption. Durability was critical for customer acceptance and automotive applications. The shock absorbers had to operate reliably for thousands of miles under harsh conditions while requiring minimal maintenance and providing consistent performance throughout their service life. October 15, 1901, the breakthrough demonstration. Gabriel introduced Semmens' hydraulic shock absorber system on October 15, 1901, using a specially modified automobile equipped with the new dampening components. The demonstration took place on a test course designed to highlight the stability advantages of controlled wheel movement. The demonstration was immediately convincing. Test drivers operated the shock absorber-equipped vehicle over road surfaces that would have caused violent bouncing in conventional automobiles, while passengers experienced smooth, controlled movement that maintained consistent tire contact and steering responsiveness. The improvement was obvious to everyone present, recalled automotive journalist Hiram Maxim. The shock absorber vehicle maintained perfect control over road irregularities that would have sent conventional automobiles bouncing dangerously out of control. It was like watching automotive stability leap forward by decades. The system's operation was sophisticated but transparent to drivers. During normal driving on smooth surfaces, the shock absorbers remained unnoticed. Only when encountering road irregularities would the benefits become apparent, as wheels remained in contact with the ground while vehicle movement remained controlled and predictable. Gabriel positioned shock absorbers as essential safety equipment rather than luxury accessories, understanding that wheel control was fundamental to safe automotive operation rather than optional comfort enhancement. Customer response was overwhelmingly positive among drivers who experienced shock absorber operation. The elimination of dangerous wheel bouncing made higher-speed driving practical and comfortable while reducing the fatigue and stress associated with uncontrolled vehicle movement. Automotive manufacturers immediately recognized the safety and performance benefits of hydraulic shock absorbers, though adoption was initially limited by cost considerations and the complexity of integrating new components into existing vehicle designs. 1902–1910 Industry Transformation. The success of Gabriel's shock absorbers created immediate interest among automobile manufacturers who recognized that controlled wheel movement was essential for safe vehicle operation at the higher speeds that automotive development was making possible. Luxury automobile manufacturers led shock absorber adoption, viewing controlled suspension movement as a competitive advantage that justified premium pricing. Companies like Pierce Arrow, Packard, and Peerless began offering shock absorbers as standard or optional equipment for customers who valued superior ride quality and vehicle control. European manufacturers embraced shock absorber technology rapidly, understanding that suspension control represented advanced engineering that enhanced their reputations for automotive sophistication. German, French, and British companies developed their own shock absorber systems while licensing Gabriel technology for immediate implementation. American mass-market manufacturers initially resisted shock absorbers due to cost concerns and customer price sensitivity. However, competitive pressure and customer demand eventually forced companies like Ford and General Motors to develop cost-effective shock absorber systems for their volume production vehicles. The technology evolved rapidly during the adoption period. Gas-filled shock absorbers were developed to prevent foaming and maintain consistent dampening. Adjustable systems allowed customization for different driving conditions and vehicle loads. Improved mounting systems simplified installation and maintenance. Racing applications drove continued shock absorber development, as competition vehicles required extreme performance from suspension control systems. Racing innovations in dampening characteristics, durability, and weight reduction eventually influenced production vehicle designs. By 1910, shock absorbers were available across most automotive price ranges and had proven their value for safety, comfort, and vehicle control. The technology that had seemed expensive and complex in 1901 became standard equipment that customers expected rather than luxury they paid extra to obtain. 1910–1920. Refinement and standardization. The period from 1910 to 1920 saw significant refinements in shock absorber technology as manufacturers developed more sophisticated systems and standardized designs for mass production efficiency. World War I accelerated development as military vehicles required reliable suspension control under extreme conditions. Hydraulic fluid formulations improved significantly during this period, with specialized oils that maintained proper viscosity across wider temperature ranges while resisting contamination and chemical breakdown. These improvements made shock absorbers more reliable and longer-lasting. Manufacturing processes were developed specifically for shock absorber production, including precision machining techniques for hydraulic cylinders and advanced sealing technologies that prevented oil leakage. These improvements reduced costs while improving quality and consistency. Automotive integration became more sophisticated as manufacturers designed vehicles specifically to accommodate shock absorbers rather than adapting existing designs. This integration improved shock absorber effectiveness while simplifying installation and maintenance procedures. International standardization efforts established common specifications for shock absorber mounting, performance, and testing that enabled interchangeability between manufacturers and simplified replacement procedures for vehicle owners and mechanics. The automotive aftermarket for shock absorbers developed rapidly, as vehicle owners discovered that worn shock absorbers could be replaced to restore original ride quality and vehicle control. This aftermarket created ongoing business opportunities for Gabriel and other shock absorber manufacturers. By 1920, shock absorbers were considered fundamental automotive safety equipment rather than optional comfort accessories. Insurance companies began recognizing vehicles with proper shock absorbers as lower risks due to improved vehicle control and accident prevention capabilities. Modern evolution and integration. Contemporary shock absorber systems are direct descendants of Claude Semmens' 1901 innovation, using the same basic hydraulic principles while incorporating sophisticated improvements in materials, design, and integration with other vehicle systems. Modern shock absorbers include features that Semmens couldn't have imagined: electronic adjustment for varying road conditions, integration with stability control systems, and magnetic fluid dampening that can change characteristics instantly. However, the fundamental function remains unchanged. Control spring oscillations to maintain tire contact and vehicle stability. Electronic stability control and advanced driver assistance systems rely heavily on shock absorber performance to maintain vehicle control during emergency maneuvers. The basic dampening system, pioneered in 1901, enables modern safety systems that can prevent accidents and assist drivers in challenging driving situations. Electric and hybrid vehicles use sophisticated shock absorber systems that must handle unique weight distributions and performance characteristics, while maintaining the smooth, quiet operation that makes electric vehicles appealing to customers. Advanced materials and manufacturing have improved shock absorber durability and performance while reducing weight and maintenance requirements. Modern shock absorbers can operate for vehicle lifetimes while providing superior dampening in all conditions. Racing and performance applications continue to drive shock absorber innovation, with developments in adjustability, responsiveness, and durability that eventually benefit all automotive applications. The competition environment provides testing conditions that accelerate technological advancement. Impact and recognition. Claude Semmens' development of hydraulic shock absorbers represents one of the most important vehicle control innovations in automotive history, transforming vehicle stability while enabling the safe operation of modern automobiles at highway speeds. The technology's social impact extends beyond comfort improvements. Shock absorbers made automotive travel safer for all passengers while enabling the development of higher-speed transportation that transformed 20th-century society and commerce. From an engineering perspective, shock absorbers established important precedents for hydraulic automotive systems that continue to influence modern vehicle development. The technology demonstrated how fluid dynamics could solve mechanical problems while improving both safety and performance. The economic impact was enormous. By enabling safe, high-speed automotive travel, shock absorbers contributed to the development of highway transportation systems that revolutionized commerce, tourism, and social mobility throughout the developed world. Shock absorbers also influenced automotive design philosophy, proving that comfort and safety improvements could be engineered systematically rather than accepted as inevitable limitations. This lesson continues to guide modern automotive development toward increasingly sophisticated vehicle control systems. The stability revolution that began with Semmens' 1901 innovation demonstrates how hydraulic engineering can solve fundamental mechanical problems while improving human comfort and safety. The smooth, controlled ride that modern drivers take for granted represents one of automotive history's most successful engineering achievements. If this story moved you, subscribe to The Car Chronicles and hit that like button. Share it with someone who needs to know that the greatest automotive innovations are often the ones that make driving safer and more comfortable, and that hydraulic engineering has repeatedly revolutionized automotive technology in ways that benefit everyone. What's your most memorable shock absorber experience? Let us know in the comments how suspension control has influenced your automotive confidence and comfort during challenging driving conditions.